Next is rational functions. Just like in our previous lesson when we had rational equations, so rational function is just an equation of ratios of two algebraic expressions or two polynomials. So what are rational functions? Let's define this one. A function f is a rational function if f of x is equal to n of x over d of x, where d of x is not equal to 0, where both n of x and d of x are polynomials. Actually, we can expand this one as f of x is equal to, since n of x and d of x are polynomials, we can write this one in a more expanded form as a sub m x to the m plus a sub m minus 1 x to the m minus 1 plus a squared x squared plus a sub 1x plus a sub 0 over b sub n x to the n plus b sub n minus 1 so we can write this one in this expanded form. Okay, since both n of x and d of x are polynomials. So example of rational functions are 1 of x is a rational function, g of x minus 1 over x squared minus x minus 6 is also a rational function. D of x is equal to x cubed minus 1 over x squared is also a rational function. R of x is equal to 2x minus 3. So linear function is also a rational function. Okay, because automatically there is a denominator 1 there and 1 is a polynomial. Okay. Also, the constant function is a rational function. Then we have s of x is equal to 5 over x plus 2 is also a rational function. Then we have, say, c of x squared minus 3x minus 4 over x minus 2 is a rational function. Then v of x is equal to x squared minus 1 over x plus 1 is also a rational function. So if it is a ratio of two polynomials, then that function is a rational function. Now, how to graph rational functions? Let's follow the steps in graphing rational functions. Simplify the expressions into lowest term because we might be able to find common factors between the numerator and the denominator, then we can cancel that out. So that's what I mean simplifying the expressions. Then finding the whole or wholes of the graph, finding the vertical asymptote, or asymptotes, then finding the horizontal asymptote, and then finding the x and y intercept, then identifying arbitrary points that would help us determine the direction of the graph. Okay, So these are the steps. So first, simplify the expression. So our function, which is 1 over x, is already in a simplified form. But our v of x, which is x squared minus 1 over x plus 1, can still be simplified as x plus 1, x minus 1 over x plus 1. Okay, so you can cancel out x plus 1 here, so that you would have x minus 1 remaining. That's what I mean, simplify the expressions. Then finding the wholes. Okay, our example here, which is f of x is equal to 1 over x, has no whole, so it's fine. But this one, the v of x, has a whole. So as you can see, x plus 1 over x plus 1 is cancelled out. Okay, it means that graph of the rational function has a whole, and the whole is x is equal to negative 1. Okay, if you equate this one to 0, you get x is equal to negative 1. So if this is your graph, okay, if you locate the negative 1 here, and what is the value of this function when x is negative 1? That's negative 1 minus 1, that's negative 2. So 1, 2. So in this part here, there is a whole of the graph. So whatever the graph, when it passes this negative 1, negative 2, it should be a whole there. Okay? It is not continuous on that ordered pair, on that point. So that's what I mean, a whole. Vertical asymptote is a vertical line where the graph approaches to it but does not touch it. Okay, does not, never crosses it. So that's vertical asymptote. For example, in this one, in this first example, our vertical asymptote is the y-axis itself. Okay, because when x is 0, that is undefined. Okay, when the denominator is 0, that particular value of x there is a vertical asymptote, meaning there is a line that passes through it that makes it the vertical asymptote of the graph. Example, this one, the c of x. Our vertical asymptote there is x equals 2. Okay, then horizontal asymptote, we have 3 cases for horizontal asymptote. What are the 3 cases? If in this case, in this presentation of the rational function, if m is less than n, then y equals 0, or the x-axis is the horizontal asymptote. Is the horizontal asymptote. Now, if m is equal to n, then x is equal to a of m over b of n is the horizontal asymptote. So let's have an example. Let's say j of x is equal to, let's say, 2x squared plus 4x minus 1 over 3x squared plus 2x plus 1. So in this case, our m is 2 and our n is 2, so they are equal. So the coefficients of these terms will be, the ratio of their coefficients will be our horizontal asymptote. So we have the horizontal asymptote there is y is equal to 2 over 3. So if this is our graph, this is our x, this is our y, then locate 2 over 3, this is 1, 2 over 3 is somewhere here, so we will have a vertical asymptote. And the graph approaches to it but never touches it. That's the horizontal asymptote. Now, if the third case, if m is greater than n, then we do not have a horizontal asymptote, but we'll have an oblique asymptote. An oblique asymptote is a diagonal line if m is 1 more than the n. So for example, c of x, okay, the c of x there, c of x is equal to x squared minus 3x minus 4 over x minus 2. So as you can see, m is greater than n, 2 is greater than 1. So this example has no horizontal asymptote, but there is an oblique asymptote. Now, how do we find the oblique asymptote? We can use division of polynomials. Okay, we can use long division or synthetic division. So let's try to graph now. We'll start from the most basic, not the linear ones, not the constant functions, but the function with a variable in the denominator. So let's graph f of x is equal to 1 over x. So again, it is already in a simplified form. As what we mentioned a while ago, it has no hole. This is our graph. It has no hole. Then it has vertical asymptote. The vertical asymptote is x is equal to 0. So we can have vertical asymptote here. The y-axis is the vertical asymptote, meaning the graph does not touch there, but it approaches there. Then, is there a horizontal asymptote? Yes, because m is less than n, and the horizontal asymptote is the x-axis itself. The x-axis. Now, is there an x and y intercept? In this case, no, since it does not touch the x-axis and the y-axis. So basically, it has no x and y intercept. Now, next step would be locating arbitrary points. You can have arbitrary points here like 1, 2, 3, -1, -2, -3. Then just substitute. So we have x, f of x. When x is 1, our f of x is also 1. Okay. Now when x is, let's use 10. When x is 10, our f of x is 1 over 10. So here, when x is 10, it's 1 over 10. Now when x is 1 over 10, our f of x is 10. So it's here. Okay. Connect the points. Okay. Now on the left side of the origin, when x is -1, our f of x is -1 here. Now when x is -10, our y is -1 over 10. So when x is -10, our y is 1 over -10. And when x is -1 over 10, our f of x is -10. So somewhere here. Then connect the points. Okay. So this one here is our f of x is equal to 1 over. Now what is the domain of this function? The domain is all real numbers except 0, because again it does not touch the y-axis. So all real numbers except 0, or you can write this one as from negative infinity to 0, or from 0 to positive infinity. Same with the range of this function. So all real numbers except 0. Another example, graph f of x equals 2x squared plus 8x plus 6 over x squared minus 9. Solution. Let's graph this one. Again, simplify. Can we simplify this one? F of x is equal to 2x squared plus 8x plus 6 over x squared minus 9. For the denominator, we can factor out 2 first. We have x squared plus 4x plus 3. Then the denominator is difference of 2 squares. So that means that's x plus 3, x minus 3. Then, can we factor out x squared plus 4x plus 3? What are the factors of 3? And when you add that one, that pair is 4. So we have x plus 3 and x plus 1 over x plus 3, x plus 1. So that's the simplified form. Next, find if there is a whole or wholes. Basically, yes, because there is a common factor. There is a common factor, the x plus 3 in the numerator and the x plus 3 in the denominator. So the whole would be x plus 3 equals 0, means x is equal to negative 3. Now, if x is negative 3, what is f of negative 3? So our f of negative 3 from this simplified form, that's 2 times negative 3 plus 1 over negative 3. Oh, no. This is x minus 3, sorry. This is x minus 3. X minus 3. Okay. So this is negative 3 minus 3. That's negative 3 plus 1. That's negative 2 times 2. That's negative 4 over negative 6. That's 2 over 3. So therefore, we have a whole in this ordered pair, negative 3, 2 over 3. Now let's draw a rectangular coordinate system. This is our x. This is our y. Negative 3, 2/3. 1, 2, 3. This is 1, 2/3 somewhere here. So this is our whole. So the graph passes through it, but does not exist in that point. Okay, it is not continuous on that point. Next is vertical asymptote. What is the vertical asymptote from this? It's x minus 3. So vertical asymptote is x minus 3 equals 0, x equals 3. So we have 1, 2, 3. Okay, let's create a broken line as indicator for vertical asymptote. So this one here is x equals 3. Then we have, is there a horizontal asymptote? Again, in this case, our m is equal to n. So therefore, our horizontal asymptote is the ratio of their coefficient, which is 2 over 1 equals 2. So let's locate 2. This is 1. This is 2. Okay. So that's the horizontal asymptote. So this is y is equal to 2. Next, let's locate if there is x and y intercept. Here you can just make a table, x, y. When x is 0, what is y? When y is 0, what is x? So from the simplified form, our f of 0 is 2 times 0 plus 1 over 0 minus 3. That's negative 2/3. Okay, this is negative 2/3. So when x is 0, our y is negative 2/3 here. That's the y-intercept. Okay, so this is 0, negative 2/3. Now when y is 0, what is our x? So f of x equals 0 means 0 is equal to 2 times x plus 1 over x minus 3. So that means x 0 is equal to 2 times x plus 1, multiplying both sides by x minus 3. That means 0 is equal to x plus 1, dividing both sides by 2. Then we have negative 1 equals x. Okay, when y is 0, x is negative 1. So let's locate this one. This is negative 1. Y is 0. X is negative 1 here. So this is negative 1, 0. So we have located already our x and the y-intercept. Next is arbitrary points. The best arbitrary points that we can get are those near the asymptotes, okay, here and near the x and y intercept. So we can have, since if we connect this one, this 3 here, okay, let's use another color. If we connect this one here, we have an idea where it's going, but we can use another point to support that one. Let's say this one 2. Okay, when x is 2, when x is 2, what is f of 2? F of 2 is 2 times 2 plus 1 over 2 minus 1. So this one here is positive over negative. So the answer is negative. So meaning it's going down. Okay, here. It's going down. Then here, let's say 10. You can use 10. This is negative. Sorry. This is negative. So if we use negative 10, what will happen? F of negative 10, that's 2 times negative 10 plus 1 over negative 10 minus 3. This is negative here, and this one here is negative, so that's positive. So here it's a positive. Okay, it's above the negative y. Okay, there. Now how about on the right side of the vertical asymptotes and the horizontal asymptotes? Right of the vertical and up of the horizontal asymptote. So we can use, say, 1, 2, 3. You can use 4. Okay, you can use 4. This is positive. If we use 4, what is f of 4? That's 2 times 4 plus 1 over 4 minus 3. That's 8. That's 5 times 2. That's 10 over 1. So that's 10. 4 is 10. Somewhere here. Okay, assuming it's here. Now how about when x is 10? Okay. When x is 10, this is f of 10 equals 2 times 10 plus 1 over 10 minus 3. This is 22 over 7. So 22 over 7, that's 3 something, somewhere here. 3 something. Okay. Now obviously, if we connect this point, now if we extend, this is 22 over 7. If we extend, if that is 100, that's f of 100 equals 2 times 100 plus 1 over 100 minus 3. So that's big enough. Okay, this is super positive here. So it's somewhere here. So if we connect the points, this is the form of the graph. Okay, again, it doesn't touch the horizontal asymptote. Okay, now this is the graph, which is f of x is equal to 2x squared plus 8x plus 6 over x squared minus 9. Okay, so we have a hole again. We have a hole. We have a vertical asymptote. We have a horizontal asymptote. We have a y-intercept. We have an x-intercept. And then we have located arbitrary ordered pairs by choosing arbitrary values of x. Now what is the domain here? The domain is from negative infinity, and then here the hole is not included. Remember, the hole is not included, and the value there is this one, negative 3 2/3. So from negative 3 union, from negative 3 to the vertical asymptote. What is our vertical asymptote? 3. Okay, union 3 to positive infinity. So that's the domain. How about the range? The range is from negative infinity to, again, the whole is not included, to 2 over 3 union 2 over 3 to what is the horizontal asymptote again? 2 union 2 to positive infinity. Okay, this is the whole thing for this graph. It's quite messy, guys. It takes a long period of time to graph, but if you know the process, if you know the step by step on doing this, then it would be easier for you, because the step by step process is our guide in graphing the function correctly. Again, do not forget these steps. Simplify first, then find the whole, vertical asymptote, horizontal asymptote, x and y intercepts, then the arbitrary points. Okay, question. So as practice problems, you can use this samples here. Where is it? You can use these samples here. You can use these samples to graph rational functions. Now, before we end this one, let's have the one with the oblique asymptote. Okay, this one, f of x is equal to, we will not graph everything, we will not solve everything. I will just show you how to find the oblique asymptote. X squared minus 3x minus 4 over x minus 2. In this case, our m is greater than n because 2 is greater than 1. So we don't have a horizontal asymptote for that, but we can have an oblique. So how do we find the oblique asymptote? We use a long division. So we have x squared minus 3x minus 4 over x minus 2. By using the long division, x squared divided by x, that's x, then multiply x squared minus 2x, then subtract. So this is negative, this becomes positive. So that's negative 3x minus 4. Then x divided by x, that's 1. To get negative 3, that's negative 3. So that's 3 times negative 3x. Oh no, this is 1, sorry. This is 1 here. So this is negative x minus 4. Then x divided by negative x divided by x, that's negative 1. So that this is negative x, this is plus 2. Then subtract, that's 0, this is negative 6. Okay, so we don't mind about the remainder. The answer here is x minus 1 plus negative 6 over x minus 2. But we don't mind about the remainder. We just take the quotient there, which is x minus 1. So therefore, our oblique asymptote is this one, y is equal to x minus 1. So if we graph that one, what is y equals x minus 1? The y-intercept is negative 1, then the rise is 1, the run is 1. Okay, if we connect this one, that is our oblique asymptote. Okay, so the graph does not touch there, but it will approach in that line. This is our y is equal to x minus 1. Okay, I will not show you the step by step. The most important part in this example is finding the oblique asymptote. Okay, so try to graph the other examples or try to find examples on the books on graphing rational functions. Question?